Hello, everyone, and welcome to the second episode in our AI and You podcast. Today is Tuesday, July 28th, 2020, and I'm your host, Vicar Saidi. I'm a computer scientist and engineer, and I'm also the author of several books. My most recent book is about artificial intelligence and is titled The Genome Affair. The Genome Affair is a work of speculative fiction. It examines what the world might be like if some of the more extraordinary capabilities forecast to be realized in AI over the next 20 or 30 years were actually realized today. The book has a particular focus on the impact AI is expected to have on world affairs and has been very well received. The book is available in ebook format for those who prefer to read on a digital device, but it's also available in a high-quality paperback edition. The Genome Affair is available on Amazon, so I hope you'll take the time to read it. Please do let me know what you think. And now on to today's podcast. In last week's podcast, I defined artificial intelligence in the context of human intelligence. I shared a simple model of the three major layers of the human brain: the Reptilian Brain, the Mammalian Brain or Limbic System, and the Cortex. I also spoke about how the human cortex had undergone a surprising transformation some 70,000 years ago. And finally, I explained that AI is attempting to mimic or simulate the cortex. I'll begin today's podcast by providing some context on how we got where we are today in artificial intelligence. As promised last week, I'll then talk more about machine learning and deep learning neural networks, while also explaining some additional terminology in the AI Lexicon that you're likely to hear. Finally, I'll share some incredibly exciting and hopeful examples of how artificial intelligence agents are being used today. Now, let's turn the clock back a few decades and take a short history lesson. I think it would be valuable to provide some background into the foundation and basis of artificial intelligence. Perhaps the birth of computer science and artificial intelligence occurred in the autumn of 1938 in Buckinghamshire, about 43 miles north of London, England, in a town known as Bletchley Park. It had been only 20 years since the end of the last destructive war in Europe, the Great War, and once again Europe was on the precipice of war with Germany. Nazi High Command in Berlin used a machine and technology known as Enigma to broadcast communications to their field offices and troop divisions expanding across the continent. Anyone could listen in on these broadcasts since they occurred over radio airwaves, but these communications were encrypted. Furthermore, the extremely large number of combinations one would need to consider in order to decrypt the messages was beyond the scope of even the brightest minds clandestinely assembled by the British government at Bletchley. Alan Turing, a brilliant mathematician from Cambridge University, concluded that breaking the code by assembling a team of mathematicians and others with a proclivity for puzzles was not the answer to their problem. He and the others knew that the longer they took to decode Enigma, the longer the war would go on and the greater the risk that the Nazis would be successful in establishing imperial rule across Europe. They knew that the death toll would continue to mount and that Europe's architecture and cultural heritage was at risk of being erased. Turing set about building what came to be known as the Turing machine, or bombe, B-O-M-B-E. It was a large electromechanical machine that could process Enigma's codes and then work to decipher them much faster than any human, no matter how bright or clever. Enigma, with its hundreds of millions of possible combinations, presented a mathematical challenge that was quite simply beyond the scope of human intelligence. It was much too much data for the human mind to hold in place and process. The Turing machine was successful in deciphering Enigma's coding scheme and was also successful in decrypting the codes used by other Axis powers, including Italy and Japan. Most historians believe that the work done at Bletchley Park shortened the length of World War II by 2 years and saved nearly 12 million lives. Additionally, Turing's efforts with his bomb machine led to the birth of the academic field of computer science and artificial intelligence. In summary, then, the goal of artificial intelligence and computing was to enable the Turing machine, and other computers that would follow in the years and decades to come, to think the way people do, but to be able to process information much faster than humans can, and while using a much greater volume and complex data set. But Alan Turing's machine received its rudimentary intelligence through a set of instructions it was to follow, a collection of rules known as an algorithm. We spoke about algorithms in the last podcast, but briefly, let's think of algorithms as a simple, or sometimes highly complex, set of instructions or orders given to a computer. This algorithm, this set of instructions, would enable the computer to perform a well-defined set of tasks, while accommodating some degree of predetermined variability. The computer could then produce a set of outputs from all the inputs it received by processing these inputs or data using the algorithm. The Turing machine and the silicon-based solid-state machines that were to follow over the next 6 decades or so could only receive their instructions, their capabilities, through such an algorithm, and they were unable to deviate from this instruction set, regardless of any need to do so. If the machine was expected to alter its methods or was required to perform additional tasks, the computer scientist would need to modify or add to the current algorithm and resubmit it to the machine. The machine was not capable of rewriting or expanding its own instruction set. The machine intelligence was not able to function in the manner that human intelligence did. It did not have the ability to adapt and grow in knowledge and understanding with the passage of time and the change of environment, as we do. The inability to present data to computers in the manner used to present data to humans, sight, sound, smell, taste, and touch, resulted in a very constrained environment. But in recent years, particularly since 2005, artificial intelligence has made tremendous progress, so much so that, along with human genetics, AI, with its seemingly limitless applications, is now considered amongst the most exciting, if not the most exciting, area of human endeavor today. So what exactly changed? In the times in which we now live, computer and data science, electronic engineering, and neuroscience are converging, and we are rapidly entering an era in which computers have a learning process, machine learning, that can attempt to at least partially mimic or simulate the organic learning process of the human, that is, neurons and synapses. As discussed in our first podcast, the typical human brain has about 85 billion neurons, far more than any other living species. These neurons are connected in a complex scheme known as the neural network. The more we read, think, and learn, the more intricate and deeply connected our neural network becomes. AI specialists are now able to mimic the learning process of the human brain in a rudimentary manner, using very large data sets, extremely fast computer processors, and a rapidly advancing understanding of neuroscience. We have now moved into the era of neural networks that function somewhat like the human brain. This is an extraordinary achievement. But most AI agents or applications today can be characterized as artificial narrow intelligence. They can learn and perform one task or a set of similar tasks extremely well. In fact, they can perform these tasks far better than humans can. Although these narrow AI are currently unable to deviate from this small set of tasks, the day when such AI agents are able to perform a wide variety of tasks as well as humans is not far away. This AI is known as artificial general intelligence. Now, let's introduce a new term you're likely to hear often when you're within the sphere of AI: singularity. Singularity is the point at which artificial intelligence and human intelligence converge. Yann LeCun, chief AI scientist at Facebook and professor of computer science at NYU, is one of the leading thinkers and practitioners in the world on AI and neural networks. LeCun and other leading scientists believe deep learning neural networks will achieve singularity by about 2040. Other thought leaders believe it may take a few more decades, but they generally agree that singularity will happen, and at that point, AI and human intelligence will be indistinguishable. Now let's expand our artificial intelligence lexicon a bit further yet. What is machine learning and deep learning? What is supervisory versus non-supervisory learning? What is reinforcement learning? And finally, what are deep learning neural networks? Well, machine learning is the computer scientist's effort to replace cumbersome and limiting learning algorithms by providing the machine with the ability to learn in a similar fashion to the human. We want to move away from telling the computer what to learn and instead teach it how to learn. So we provide audio and visual input to the machine and it learns on its own, much like we might teach a young person. We can supervise that learning and reinforce the computer's behavior. For example, if we're trying to teach the computer to recognize a cat, we present it with many different images of cats so it can learn what it looks like. Then, when we present it with a new image of a cat that it hasn't previously seen, if the computer recognizes that the new image is of a cat, it gets a point. In this scheme of supervised reinforcement learning, the computer quickly realizes that getting points is desirable, and after many thousands of examples, its success rate in identifying cats correctly approaches a level that is higher than most humans. But narrow AI agents are becoming extremely sophisticated. We now have narrow AI agents that require no supervision. We are proving this in very complex game theory applications, such as in the ancient Chinese board game Go. I'll share this example with you in our next podcast. The final term in the AI lexicon I wanted to share with you is deep learning neural networks. I suspect you already understand the neural networks part of the term. It's an attempt to rudimentarily mimic the neural network in the human brain. The deep learning prefix simply means that the computer is taking a hierarchical approach to problem solving. It is using several tiers or layers of processing to break down complex tasks into subtasks in order for it to rapidly and efficiently produce its output. I'll share a few fascinating examples of artificial narrow intelligence, these deep learning neural networks, with you now. Recently, researchers at Stanford University's Department of Computer Science have been working on a fascinating application of deep learning neural networks in the area of radiology. They have developed an AI application that can identify pathology in X-rays. The researchers use a set of 100,000 X-ray charts they received from the National Institutes of Health. Some charts had no pathology, while others did present some pathology. The NIH also provided comprehensive information regarding the nature of the pathology. The Stanford AI application was trained on these 100,000 charts and was then tested by showing it new charts. The tests demonstrate that the AI was accurate 33% of the time, whereas radiologists trained at Stanford Medical School were accurate 95% of the time. The researchers obtained a second data set of 200,000 additional X-rays from Stanford University's medical school and continued to train the AI application with this new data set. the AI application is now 98% accurate in identifying pathology in the X-rays, along with the nature of the disease. If we think about all the rural and urban communities in the developing world, or in the numerous conflict zones where the need for effective diagnosis exists, an AI application like the one from Stanford will be of inestimable value. There may be diagnostic equipment available in distant communities, but it's unlikely that these communities will have radiologists available with the capacity or skill to effectively read so many X-rays. In fact, the sad reality is that amongst the world's population of 7.5 billion, only 2 billion have access to medical imaging and subsequent professional diagnosis. Another fascinating recent application of AI in the domain of health sciences is in the diagnosis of Parkinson's disease at the University of Birmingham in the UK. I lost my father to Parkinson's almost 3 years ago, so this application of AI is of particular interest to me. During the early stages of the disease, it's very difficult to diagnose Parkinson's. Nevertheless, there are a few signs, albeit very subtle. One of these signs is a nearly undetectable change in gait. If we plot our gait on a chart, it resembles a typical sinusoidal waveform with consistent amplitude and frequency. But in a Parkinson's patient, there are minor variations in both the amplitude and the frequency of the waveform. By installing this AI application on a person's smartphone and having them carry the device for a few days, the phone will collect a sufficiently large data set that can then be processed by the AI application. A similar variation in Parkinson's patients occurs in the human voice, and an AI application is being developed to monitor these variations via a smartphone application as well. The University of Birmingham AI application can identify these previously undetectable signs and diagnose the irregularities versus the normal gait, as well as changes in the voice, with 99% accuracy. Another medical science-related AI application likely to emerge in the near future is in the area of human genomics. Through the Human Genome Project at the turn of the century, we have been successful in mapping the human genome. But much work remains to be done. For example, we know that human attributes and characteristics have their basis in our genes. But unfortunately, there isn't a simple one-to-one correlation between human attributes and our genes. It's a much more complex relationship in which many genes, perhaps 1,000 or more, are involved in influencing a single human attribute or characteristic. It is a one-to-many relationship. The reverse is also true. One gene may influence many human attributes and characteristics. Not surprisingly, it is unlikely that human intelligence will be successful in decrypting this wonder of our species without the help of artificial intelligence and quantum computing. We'll discuss quantum computing in a future podcast, since it's an incredibly important enabling technology for AI. In summary, as you can imagine, the scope of opportunity for applying artificial intelligence to problems in human health that were not previously possible is limitless and humbling. We can expect to see extraordinary progress as a result of the application of AI in the health sciences over the next few years. But AI can also provide countless applications to improve our daily lives. For example, you can now place your smartphone over a page in a book or magazine, before a street sign, or even a menu in a Michelin-starred French restaurant, where you might feel your high school French is failing you and you're unable to understand the various bewildering menu choices. Well, there's nothing to fear. The AI agent instantly translates any of these scenarios for you. One of my favorite examples of narrow AI has to do with a very ancient Chinese board game called Go. A Google company in London called DeepMind recently developed an artificial intelligence application called AlphaGo that has learned to play this ancient Chinese board game. Go is played on a square board with black and white discs resembling checkers, although it's considerably larger than a chess or checkerboard with dimensions of 19 by 19 squares. Go was first developed in China some 4,300 years ago and has been played in China, Japan, and South Korea ever since. It is played professionally by players ranked up to level 9, and there are books and courses taught around the game, its philosophy, and play strategies. It's a relatively simple two-player game, but the number of combinations that can unfold on the board is 10 to the power 170. The number of atoms in the universe is 10 to the power 80, so this is really extraordinary. In 2016, DeepMind and their narrow AI agent, AlphaGo, challenged the world grandmaster, a young South Korean man named Lee Sedol. AlphaGo had learned to play the game simply by studying games that were posted on the internet. In the next episode of the podcast, I'll share more about DeepMind's experience with AlphaGo, and I'll also share some disconcerting examples of narrow AI today. I'll also talk about the profound impact such powerful technologies can have on societies that possess them and those that do not. Thank you for spending some time with me. I'm trying to follow the TED Talk format, and so I'm keeping these podcasts to about 20 minutes. Let me know what you think. I hope you'll find these insights into artificial intelligence helpful, and I hope you'll read my book, The Genome Affair. Until next time, then, this has been the AI and You podcast with author Vicar Saidi.